In this video, I'm going to show you a way to determine the analog to digital conversion's accuracy from the 10-bit results. This will give you a metric on how well other components are used, like capacitors, and other programming functions such as the ADC sleep mode. So let me describe the process of the ADC and measurements. Over time, you will get the ADC will give you a measurement. Let's say this is the measurement on the scale of 0 to 1023. And this is going to be exaggerated quite a bit. So this would be our first measurement. Maybe our next measurement would be here. Maybe the next measurement would be here. Maybe the next measurement will be here. And let's just say that this is a 200. This is around 200. And maybe this measurement came out to be 210. And this one is 190. And then this one is around 205 or 203. And we want to determine the displacement, or the difference between the first one and then the next one, and then the difference between this one and then the next one, and then the difference between this one and then the next one. And what we'll get is a sort of a delta between each sample. So a delta to this, for this one would be 10, and a delta to this one would be 20. And then a delta between these two would be 13. And then we can take all of those deltas and we can add them up to see what our final result would be over many samples. So if we were just going to take 3 samples, this would be 10 plus 20, 30. So the samples over time would be equal to 43. We can increase the number of samples if we want to get more samples, or we can decrease it. But as long as when we're comparing two different processes with maybe a capacitor or something else, we would want to use the same number of samples to determine what reading we get. And we would want the item that is being read to be stable, so both of those tests will be fairly done. In contrast to this, the number 43, let's look at an example that we would have maybe a more less noisy signal. So let's say we're starting at 200 again. So our first point is 200, and maybe the next point is 201. And then the next point would be 200 again, and maybe the next point would be 199. And the difference between this would be, this is 1, this would be another 1, and then this would be 1 again. So we'd have 3 as the overall difference. And obviously the lower number you get, the more stable the signal is. In the circuit we had a capacitor in this location, and I removed it for this part of the demonstration, so we can see what the deflection is without the capacitor. We'll try it with the 10 UF capacitor, and then we'll try it with the 100 UF capacitor. Let's write some code that shows the difference between the previous result and the new result. We already have the new result. This is the 10-bit results. Now we need to create the variable that will grab the previous results. And this is also actually the previous results. It's the same variable, but we're going to store it in another variable, so it will remember it when we come back to this point the next time. We will call this variable previous results, or previous result. And we're going to make that equal to the 10-bit results. This may seem a little bit confusing at first, but we're going to save the deflection, or determine the deflection, in between these two, this assignment and this assignment. So, and we're going to call that deflection. First, let's declare this variable. So let's copy it, and we'll make it a global variable because we need it to save the results, even though it's outside of the scope of this routine. So we'll make it an 8-bit integer, and we'll call it previous result, and we'll assign it a 0. We will also need to make it a volatile variable, so the compiler is not going to optimize this out. It's a good idea to use the static volatile anytime you're trying to use a variable within an interrupt. This is just saying to the compiler, please allow this variable to be active throughout the entire execution of this program. Okay, so let's create the actual deflection variable. And I'm calling it deflection. It could be called delta, it could be called difference. I just like the word deflection because it's like a rubber band deflecting. And deflection is going to be equal to the difference between previous result and 10 bits result. And the deflection will equal this variable, which is the new result, the current result, and it's going to be subtracted by the previous result. When there is a request to make a conversion from analog to digital, it's going to go into this routine and it's going to calculate the current ADC results, which is the 10-bit results. It's going to show that to you on the LCD, and then it's for the first time it's not going to give you, it's not going to have a previous result. It's going to have 0 as previous result. So it's just going to, the deflection is just going to be equal to the 10-bit result. And you'll probably see a very large number happen right at the beginning when you first turn the LCD on. So you'll want to disregard the very first number. And then the previous result is going to equal the current one. And then we're not going to do anything else with the routine except for starting another conversion. So when it comes back and it's completed another conversion, and we're starting back to the beginning again, we will have a previous result from the last time it took a result that was the current before. And then we'll go in and get a new current, and then this new current will be showing on the LCD, and then we'll have a valid deflection because we'll have a previous result. And then we get the previous, we do this whole thing over again, and we make the previous result equal to the current result, and then it continually goes looping until we stop the controller. So we want to show the deflection on another line. So let's go ahead and create another send an integer to Mr. LCD. And we'll put this on the next line, on the second line. So we'll do number 2. We don't know where it's gonna, where it needs to be yet because we wanna put some kind of title for what we're gonna be putting here. And let's change this. This is not gonna be the 10-bit results. It's going to be equal to deflection. Okay, and let's go ahead and put in the title for this one, and we'll just call it deflection. It looks like it's at the same location, so it does equal 13. Now there's one problem with this, and the issue we're going to have is sometimes this deflection is going to be a negative number, and we don't want negative numbers. We always want this to be a positive number. We want to show the difference between the previous result and the current result. We don't want it just to be, if the 10-bit result was lower than the previous result, we would get a negative number. So let's put in a condition that states if the deflection is less than 0, which is a negative number, then let's do the reverse. Let's make it equal to previous result minus the 10-bit result. We'll just put previous result in the beginning. Then we'll subtract 10-bit result. So now we'll always have a positive number written to the screen, and we can also use that in our summing up of all of the deflections for so many samples. No, I forgot to put this on the second line. We need that on the second line. Okay, so since we're talking about the number of deflections, how many samples we want to collect, and then show the total deflections, let's create another variable. Actually, this one, we might want it a 16-bit. Actually, I'm just going to make it an int because this may be a large number. If we wanted 1,000 samples or more than that, we would have quite a bit of, we would have quite a large number to deal with. So let's use the int, and we're going to say total deflection over time. And we'll start out with 0 on that one as well. And over here, I want to start summing this up. So we're going to take the new variable that we created. We'll copy it, paste it over here, and we'll have this equaling to itself plus the deflection. So now we have this, every time this iterates and has new results or new conversions, this total deflection over time will keep adding itself to the deflection. So this will grow larger and larger, incrementing itself by the deflection. We can also write this same line like this, this is the same as saying total deflection over time equals total deflection over time plus deflection. So let's go ahead and count the number of deflections we want to consider. How many samples do we want in this total deflection over time? we need a counter for this. So we need something that will count the samples as we go through. So let's create another integer. Not actually, this will be a 16-bit integer. So because we may go over 255 counts. Static volatile, and we'll make it 16 bits, and we'll call it sample count. And we'll start off with 0 with that as well. These zeros actually aren't necessary, but it's good practice to put them in. Okay, so let's, right over here, we're going to have, every time it does a conversion, we'll have it incrementing sample count every time. And that's another way of saying these two lines are equivalent. This is just a shorthand way of saying increment sample count every time we go through this. Every time this statement is executed, sample count will equal itself plus one more, plus the number 1. So now we need to have a condition when sample count gets to the number that we desire it to stop counting and to stop adding to the total deflection over time. So if sample count, and I'm going to start out with 100. So if it equals to 100, I'm going to say equals or greater than 100, greater than or equal to. We're going to have code block. And first what we want to do is we want to put on the screen, or put on the LCD, the actual variable, the actual sum, total of all the deflections. So let's steal this line so we don't have to retype it all. And we're going to display this variable, and it's going to go on the third line. And then we're going to, and this actually could go to about 6 digits, so depending on what number we're using here. So we'll try that. We don't actually know how long it's going to be, but we'll see what happens. And then we need to make total deflection over time go back to 0. So it can start from 0 again, and also sample count needs to be 0. So it can start counting all over again and then get up to 100 again, and then display another total deflection over time. We actually have the option of actually displaying the count as well. We could actually do that. That sounds like a good idea. So let's do that. While it's counting, we'll know which iteration it has gotten to. There's a lot of stuff being displayed on the LCD at one time, but it actually will be fine. There's a lot of information. It doesn't really matter how much information. If we start seeing it get too slow, then we can take something out of the of displaying the LCD. So actually, let's make this one go on the 4th line, and let's make a title for this first. So the total deflection on the 4th line. We'll come back up here, create the title, and we will go on the 4th line, and we'll say sum of I'll just call it total, because I don't want the title to be too long. And then on the 3rd line, we'll call this sample count, or I'll just call it the count. And this will be on the 3rd line. And then we will create the sample count on the LCD. Let's put it after it's incremented. Not that it'll make any difference, because it'll go too fast for us to see anyway. Alright, so this is going to be on the 3rd line, and we'll just display sample count. I just noticed that I did not declare my variable deflection. And deflection is not going to be a very large number. So I'm going to make it an 8-bit number. I guess it could be more. Actually, I'm going to do it 16, because it could be if the sensor that I'm using was above 1000, it could go up to 1023, 1024. Then it would have a 10-bit equivalent number. So the closest one I can get for declaring is a 16-bit. And this is backwards. I have to have the greater than symbol before the equals. In some programming environments, if you type it like this and then you ended your statement, it will automatically correct it for you. So I'm getting spoiled with other environments. Okay, so let's see where we should put the deflection. Oh no, we already have that. Yeah, we have to put the count at 1, 2, 3, 4, 5, 6, 7, 8. Let's put on the 8th position. And then we have total 1, 2, 3, 4, 5, 6, 7, 8 as well. Okay, and it looks like our previous result, since our previous result is going to equal the 10-bit, I don't know why I have an 8-bit number here. I'm going to use a 16-bit number. If you notice the uint 16 and deflection being less than 0, this is actually not possible. The 16-bit integer declaration cannot be a negative number. So we need to change this to a regular integer. Now this variable can be less than 0, and we'll be able to execute this portion of the condition. Let's try the code, make the code and program it to the controller and see what happens. So this is the LCD showing all of the information, and you can see that, notice a couple things, that the count is going so fast you can't even see it. So I'm probably just going to eliminate that, make the program a little shorter. And you really can't see the deflection, but you can see that there is either 1 digits or 2 digits. You can see that there is a spattering of a second digit there, so that shows that the deflection is actually greater than 10 in some cases. So let's go ahead and change the program, make it a little cleaner. I'll probably keep the deflection, and I'm going to remove the count. Okay, let's remove the LCD presentation of the count. That was on the 3rd line. We can bring the total deflection over time to the 3rd line, and we can get rid of the count here, and then bring this to the 3rd line as well. I also want to increase the sample count maybe to about 300, because it was like going over the screen quite a bit, quite rapidly, and I was getting just a kind of a small number. I would like to see larger numbers to get a really good indication of how well we have reduced the noise. So let's reprogram the controller and see what happens. Okay, we have reprogrammed it to remove the count line, since we couldn't see it anyway. And now we have just 3 lines. You can see the deflection. Actually, I kind of see it getting into the 3rd digit, but I think it's just this 2 digits. And that's not very good accuracy. That's not very good resolution, because, and that's probably mostly due to the noise that's introduced in this particular sensor. Some of the noise could be coming from the actual prototyping environment, the breadboard itself, because there's a lot of metal underneath this, and it can receive a lot of interference. So there could be a lot of noise there as well. So we can see that the numbers are in the 3000s, about 3300, 3500, 31. So it's probably about an average of around about 3200. Let's see what happens when we put in a 10 microfarad capacitor. I'm going to turn it off. I'm going to put in the capacitor positive side from pin AD0 and negative side to the ground rail. So let's see what happens with the samples and the deflection. Okay, the total now is down to 460, and we're taking, and you can also see that there's only 1 digit here, and I can see maybe a maximum of 3. I don't think there's a 4 in there, but 450, 435, and we're only taking 300 samples, so we're really only missing 1 in a 10-bit number. We're only sort of getting maybe 9 bits out of this. We're getting about 9 bits of resolution because of the really we're only off about one out of 2 numbers. So the deflection would only be maybe 0, maybe 1, maybe 2. Very seldom it would be 3. Now let's try putting in the 100 microfarad capacitor. And I'm going to put it in the same way. Positive side to the ADC pin and negative side to the ground rail. It's always good to confirm, because these capacitors can be destroyed if you put it in backwards. Plug it in. Okay, we're getting around 400, 450, 380. So we're getting kind of an average of about 410. So it's not that much better using a 100 microfarad capacitor. It's a lot higher capacitor value, but it doesn't seem to be smoothing it out as much or as much as we would think it would. And from the last video, we knew that there was a lag when we moved the sensor. When we tilted the sensor to get a reading, we would see a lag. I'm tilting it up and I'm tilting it down now. And there's actually quite a bit of lag. So we don't want to use this capacitor. The 10 UF seems to be sufficient. Now we're going to look at putting the ADC in sleep mode and see if that helps. There is a noise cancelling technique that is recommended by the datasheet to put the microcontroller into a sleep mode while there is a conversion going on, because there are about 3 different clocks that are running inside of the microcontroller that are essentially really noisy to a lot of the functions. And if there's other functions going on, that could also introduce noise. So there is a register that controls the sleep modes, and there's one called ADC Sleep Mode, and you can also use the idle mode if you wish. Both of them will work for doing conversions. Let's take a look at the data sheet to see what we need to set to invoke these features. Okay, in the data sheet, most of the ADC stuff is in the 200 range. There is a section of the ADC where they talk about noise cancelling techniques, which really discuss how the ground plane has to be set up when you're doing a printed circuit board. Also, what you need for capacitance and inductance. There's another location where it talks about ADC noise canceller, and it talks about the ADC noise reduction and idle mode. There is a specific mode called ADC Noise Reduction Mode, and what it does is it puts the CPU, it puts the AVR core into sleep mode and reducing the noise while the ADC does a conversion. When we're doing this, we need to make sure we're doing single conversion mode. We also need to make sure that the ADC is enabled. So we need to make sure the ADC is enabled. That's the first thing. We also need to make sure that the single conversion mode is selected, and we also have to make sure that the ADC conversion complete interrupt is enabled. This number 3 is really just precautionary information on what could happen if you have other interrupts. We won't worry about that right now. Now let's go see how you can actually introduce the noise reduction mode. It doesn't give you any information in this location on how to do that, or it doesn't give you any links to where to find it in the data sheet. And this data sheet is pretty long, but you can find it if you do a search using the Control F. So if you go to somewhere around 30, yeah, it's right here. On page 32, there is information on how to set the ADC noise reduction, and that is setting 1 to SMO. It also said that we can set it up in idle mode. We're going to go ahead and use the ADC noise reduction mode, but we also have to make sure that we enable the sleep as well. So there's two bits we need to set. It's the SM0 bit, which is right here, and it's the SE bit, which is right here, number 7. And we're going to be setting them in the MC-UCR register. So let's go back to the program and do that. First, it said that this had to be enabled first, the ADC. So let's put the command here, MC-UCR. Let me make sure, MC-UCR, yeah. And we're going to do an OR operation, and we're going to set the SM0 bit, which is turning on the ADC noise reduction mode. That's the SM0, just confirming. And then we wanted to actually enable the sleep mode. MC-UCR or equals SE for sleep enable. The other requirement that we had for the sleep mode to be invoked is that the ADC conversion complete interrupt is executed if the ADIE bit, which we have set, is set, and the I bit and SREG. And this right here is just the global interrupt, which is here. So we have this set, which is the ADIE, and we have the global interrupt set. So that means that we need to put this below the global interrupt. Control X, just to make sure that that is going to execute correctly. And we're following the datasheet's instructions. So the way we have it set up here should invoke the sleep mode while we are doing a conversion. And it also said that it will start converting after we have set the single conversion mode. It will automatically start a conversion only after the CPU has stopped or has gone into a sleep mode. Let's see if this works. Okay, the sleep mode has been invoked. It's in the 400s, 300s, and we're using the 100 microfarad capacitor. I'm going to remove that and put in the 10 microfarad again. Okay, that's it. I'm going to turn it back on. And we're getting similar results as from the 100 microfarad. So it doesn't look like the sleep mode is actually making a difference. And it's most likely because of all of the interference we have on this board here. This really should be set up as a PCB, as a printed circuit board, with the ground plane, the analog ground plane set up correctly, and all of these traces coming from the sensor and from all of our power should be as short as possible. So this is not really the environment to get everything really quiet and reducing the noise. We can address that at a later time. But we have been successful in calming the sensor and making the sensor a little bit quieter. So that's how to measure the accuracy of your ADC, analog to digital converter. We can try this again when we get a PCB later on in the future. But you should be able to hook up any sensor that uses analog voltage ranges to your microcontroller and get it to read. We'll be investigating more sensors with analog readings. We'll also be investigating more sensors that produce different types of readings. Thank you for watching. If you are following along with these experiments or producing successful projects on your own, helped by these tutorials, please let me know using the Contact Us page on the newbiehack.com website. I would like to feature these on the website to benefit and motivate others to join this creative field. Thank you.